Shelves. The torpedo-shaped vehicle is lowered through boreholes drilled directly through hundreds of meters of ice, then navigates autonomously through the freezing water below, recording temperature, salinity, and current speed while capturing video of the ice's underside. Sending equipment into these under-ice environments carries genuine risk, since the robot operates far beyond any possibility of physical retrieval if something goes wrong, tethered only by a thin communications cable back to the surface team above. The data it has managed to gather represents some of the only direct, up-close observations scientists have of exactly how warm water interacts with the ice at the specific boundary where melting actually happens, information that satellite observations alone simply cannot provide. Robert Larder has been careful to explain what is actually driving all of this warm water toward the glacier in the first place. According to Larder, it isn't simply a matter of the ocean getting warmer in a straightforward, uniform way. It has more to do with how ocean circulation itself is changing, specifically shifts in the southern hemisphere's westerly wind patterns, which are pushing warmer, saltier water up from the deep ocean and directing it toward the Antarctic coastline. Those wind pattern changes, Larder noted, are themselves part of the broader pattern of climate change scientists have been tracking across the entire planet. It's important to be clear about the actual timeline here, because headlines about a Doomsday Glacier can easily make this sound more sudden than it really is. Losing the eastern ice shelf this year does not mean Thwaites itself will collapse next year, or even within the next decade. A structure this larger, simply takes far longer than that to fully disintegrate, and researchers expect any full-scale collapse to unfold over centuries, not years. What losing the ice shelf actually means is that one of the mechanisms slowing the glacier's retreat is being removed, allowing Thwaites to potentially retreat, and lose ice faster than it has been already. That distinction matters, because some of the most extreme, most catastrophic scenarios once floated around Thwaites now look somewhat less likely than scientists originally feared. One particular worst-case scenario involves something called marine ice cliff instability, where increasingly tall, unstable ice cliffs collapse in a runaway chain reaction as more ice breaks away and exposes even taller cliffs behind it. Computer modeling published in 2024 suggested Thwaites may not actually be vulnerable to this specific failure mode, though researchers caution that more work is still needed before that possibility can be fully ruled out. Still, even without that most extreme scenario playing out, the more conservative long-term projections remain genuinely alarming. One recent study published in the journal Geophysical Research Letters projected that Thwaites could be losing somewhere between 180 and 200 billion tons of ice per year by 2067. Separate research tracking 2 decades of fracturing within the eastern ice shelf found that the shelf's structural integrity has been steadily compromising through a 2-phase pattern, long shear fractures expanding first, followed by a sharp spike in smaller fractures, spreading throughout the ice. That same study projected the glacier's baseline could retreat at a rate of nearly a kilometer per year over the next 4 decades. Hilmar Gudmundsson, a glaciologist at Northumbria University, who has spent years modeling Thwaites' potential collapse, described a shift in how confident researchers have become about the glacier's long-term trajectory. According to Gudmundsson, the scientific community has moved from a place of genuine uncertainty about whether this kind of unstable, self-reinforcing retreat could happen towards something closer to near certainty that it eventually will, if the glacier's grounding line, where the ice meets the seafloor, continues retreating as current trends suggest. None of this is being treated as an inevitable, unstoppable outcome by the scientists actually studying it. Researchers continue to emphasize that reducing global carbon emissions could still meaningfully slow this process down, even if it can't fully reverse. Change is already set in motion. The challenge is that current emissions trends are moving in the wrong direction, with global fossil fuel emissions reaching record levels last year and showing no clear sign of reversing course in the near term. Climate researchers studying Thwaites are careful to distinguish between the parts of this process that already appear locked in based on how far the glacier's retreat has already progressed, and the parts that remain genuinely open, where continued emissions choices made over the next few decades could still meaningfully affect how quickly and how severely the worst outcomes actually unfold. There's also a broader concern tied directly to Thwaites' role as a structural pillar for the entire region. Scientists frequently compare removing the ice shelf to pulling a goalie late in a hockey game, opening up the rest of the ice sheet behind it to flow toward the sea far more freely than before. Given that the broader West Antarctic ice sheet holds enough frozen water to raise global sea levels by more than 10 feet. If it were ever to fully destabilize, researchers are treating Thwaites not just as a concerning glacier on its own, but as an early warning indicator for a much larger, much slower unfolding process across the entire region. Climate scientists often describe systems like the West Antarctic ice sheet using the concept of a tipping point, a threshold beyond which change becomes effectively irreversible on any timescale that matters to human civilization, even if the original cause of that change were somehow reversed. Once a large glacier's grounding line retreats past a certain point on unstable, downward-sloping bedrock, the physics of the system itself can take over, with the retreat becoming progressively easier to sustain even without any further increase in ocean temperature. This is part of why researchers like Gudmundsson describe the science shifting from uncertainty toward near certainty about eventual instability, since the concern isn't only about how warm the ocean becomes, but about whether the glacier has already been pushed past a structural threshold from which recovery becomes physically implausible. Right now, in one of the most remote and hostile places on Earth, something is happening that scientists have been watching for years, almost afraid to see it actually arrive. Antarctica's Thwaites Glacier, nicknamed the Doomsday Glacier, is about to lose the one thing that has been slowing its collapse. And according to the researchers tracking it closely, this isn't a distant future scenario anymore. It's happening this year. Let's start with why this specific glacier earned such a dramatic nickname in the first place. Thwaites is genuinely massive, roughly the size of Florida, more than 6,500 feet thick in some sections, and 75 miles across at its widest point, making it the widest glacier on the planet. But its size isn't really what makes it dangerous. What makes Thwaites the single most closely watched glacier in the world is its role as a structural pillar, holding back a much larger portion of the West Antarctic ice sheet from sliding into the ocean. Scientists have been formally studying Thwaites through a dedicated international research effort since 2018, when the International Thwaites Glacier Collaboration, a joint program between American and British researchers, first launched. The decision to fund a multi-year, multi-million-dollar research campaign focused on a single glacier reflected just how seriously the scientific community had already come to view Thwaites, even years before this latest round of alarming headlines. Since that collaboration began, researchers have deployed a wide range of tools rarely used together at this scale, including autonomous underwater vehicles, ocean-going icebreakers capable of pushing through some of the thickest sea ice on Earth, and networks of GPS sensors anchored directly onto the ice to track its movement in real time. That sustained, coordinated effort is exactly why scientists today have such a detailed, high-resolution picture of what's happening beneath and around Thwaites, compared to many other Antarctic glaciers that receive far less consistent attention. Think of Thwaites less like a single glacier and more like a cork in a bottle. Behind it sits enough frozen ice to raise global sea levels by roughly 10 feet if the surrounding ice sheet were ever to fully destabilize. Thwaites alone, if it disappeared entirely, would add a little over 2 feet to global sea levels. But scientists have spent years warning that the real danger isn't Thwaites acting alone. It's what happens to everything behind it once this particular pillar gives way. To put that 10-foot figure in perspective, even a fraction of that rise would fundamentally reshape coastlines around the world. Low-lying coastal cities like Miami, London, and cities across Bangladesh and the Pacific Islands are already grappling with more modest sea level increases tied to melting ice and warming oceans worldwide. A rise measured in feet rather than inches would push storm surges, high tides, and routine flooding events far beyond what current coastal infrastructure was ever designed to handle, forcing difficult and expensive decisions about seawalls, relocation, and which areas remain realistically defensible over the coming decades. This is exactly why a single glacier on the opposite side of the planet from most major population centers has become such a closely tracked indicator for climate researchers and coastal planners alike. For years, Thwaites has had a natural brake system helping to slow this process down, a floating extension of ice called the Eastern Ice Shelf, sitting right at the glacier's mouth where it meets the ocean. This ice shelf functions almost like a doorstop, wedged in place partly by a raised ridge on the ocean floor, physically restraining how quickly the glacier's ice can flow out into the sea. As long as that shelf held together, it acted as a genuine buffer, slowing the rate at which Thwaites could dump ice into the Southern Ocean. Understanding the difference between a glacier and an ice shelf helps explain why losing this particular structure matters so much. Thwaites. Glacier itself begins on land, moving slowly under its own weight the way all glaciers do, gradually sliding toward the coast under the pull of gravity. But because Thwaites extends so far out to sea, part of it eventually pushes past the underlying bedrock entirely and starts floating directly on the ocean's surface, forming what's known as an ice shelf. That floating section is still physically connected to the grounded glacier behind it, which is exactly what allows it to act as a brace, pressing back against the ice trying to flow outward from land. Remove that floating brace, and the grounded ice behind it loses much of the resistance that had been slowing its movement toward the sea. That buffer is now breaking apart. According to Robert Larder, a marine geophysicist with the British Antarctic Survey, who coordinates the UK side of the international Thwaites Glacier collaboration, the shelf is very likely to disintegrate before the end of this year. Larder has been blunt about what the satellite data is showing. The last remaining ice shelf in front of the glacier is poised to disintegrate, and while scientists don't yet know exactly how the breakup will unfold, they are confident it is coming. Satellite imagery already shows the shelf fracturing in exactly the places researchers were most worried about, right where it anchors against the underwater ridge and along the front edge where it meets the glacier itself. Christian Wild, a geophysicist at the University of Innsbruck, who has been tracking the shelf's movement, described watching large areas simply falling apart, comparing the pattern to a windshield, shattering into a spreading web of cracks. Karen Alley, a researcher at the University of Manitoba, who studied the same ice back in 2019 and 2020, said the recent satellite images barely resemble what she remembers observing just a few years ago, with huge gashes now visible where there used to be none. The speed of this change is what has really caught scientists off guard. Movement on the western side of the shelf has roughly doubled over just the past 8 months, and the flow rate of the ice shelf itself has nearly tripled. Between January 2020 and January of this year, now moving at just over 2,000 meters annually, a pace multiple researchers have described as simply not normal for a structure this size. To understand why this is happening, you have to look at what's actually attacking the glacier from below. Thwaites sits on bedrock that dips downward as you move inland, meaning warm seawater can push in underneath the ice and continue melting it from beneath, even as the ice above stays intact. This year, researchers using a combination of ice-breaking ships and an underwater robot named Icefin confirmed that seawater is moving more than 6 miles beneath the glacier itself, actively accelerating the melt happening at its base. The same research also traced Thwaites' current retreat back further than expected, showing that its decline likely began as far back as the 1940s, possibly triggered by a powerful El Nino event that altered ocean conditions along the Antarctic coast. None of this is being treated as an inevitable, unstoppable outcome by the scientists. Emissions could still meaningfully slow this process down, even if it can't fully reverse changes already set in motion. The challenge is that current emissions trends are moving in the wrong direction, with global fossil fuel emissions reaching record levels last year and showing no clear sign of reversing course in the near term. Climate researchers studying Thwaites are careful to distinguish between the parts of this process that already appear locked in based on how far the glacier's retreat has already progressed, and the parts that remain genuinely open, where continued emissions choices made over the next few decades could still meaningfully affect how quickly and how severely the worst outcomes actually unfold. There's also a broader concern tied directly to Thwaites' role as a structural pillar for the entire region. Scientists frequently compare removing the ice shelf to pulling a goalie late in a hockey game, opening up the rest of the ice sheet behind it to flow toward the sea far more freely than before. Given that the broader West Antarctic ice sheet holds enough frozen water to raise global sea levels by more than 10 feet, if it were ever to fully destabilize, researchers are treating Thwaites. Climate scientists often describe systems like the West Antarctic ice sheet using the concept of a tipping point, a threshold beyond which change becomes effectively irreversible on any timescale that matters to human civilization, even if the original cause of that change were somehow reversed. Once a large glacier's grounding line retreats past a certain point on unstable, downward-sloping bedrock, the physics of the system itself can take over, with the retreat becoming progressively easier to sustain, even without any further increase in ocean temperature. This is part of why researchers like Gudmundsson describe the science shifting from uncertainty toward near certainty about eventual instability, since the concern isn't only about how warm the ocean becomes, but about whether the glacier has already been pushed past a structural threshold from which recovery becomes physically implausible. Researchers stationed in Antarctica this year have described an almost constant state of vigilance while tracking these changes, checking satellite imagery daily to see how quickly the fracturing is spreading. Teams have also been working directly on the ice itself, attempting to place monitoring instruments beneath the glacier's main trunk to gather direct measurements of water, temperature, and flow speed. Even when instrument deployment hasn't gone entirely as planned, researchers have still managed to confirm that the water moving beneath Thwaites is both warmer and faster flowing than earlier models had predicted, adding yet another piece of evidence pointing toward an accelerating rather than slowing retreat. Working in this environment presents challenges that go far beyond the science itself. Field teams operate in one of the most logistically difficult regions on Earth, often flying in aboard specially equipped aircraft capable of landing directly on ice runways. then living in temporary camps where temperatures regularly drop far below anything most people ever experience, all while hauling scientific equipment across crevasse-riddled terrain that shifts and crackles beneath their feet. Drilling access holes through hundreds of meters of ice to deploy instruments like IceFin can take days of careful, physically demanding work, all within a narrow weather window before conditions become too dangerous to continue. Every successful measurement gathered under these conditions represents a genuine logistical achievement layered on top of the scientific one, which is part of why researchers describe each field season at Thwaites as both scientifically vital and physically grueling in equal measure. If stories about the science behind Earth's changing ice sheets and what they mean for coastal communities worldwide matter to you, hit like on this video and subscribe, because Thwaites' situation is actively developing, and researchers expect major updates as this year's ice shelf breakup continues to unfold. Is losing its last natural break, and the scientists watching it happen are doing exactly what they've done for years, gathering every piece of data they can, trying to understand not if this will eventually reshape coastlines around the world, but how quickly and how far that change will ultimately reach. Whatever happens with the eastern ice shelf over the coming months, one thing about this story is already clear. The question surrounding Thwaites has genuinely shifted. Unfold, and what portion of it can still realistically be slowed through global efforts to curb emissions. For coastal communities, thousands of miles away from Antarctica's frozen coastline, the answer to that question, still being written in fractures spreading across a remote ice shelf right now, may end up shaping decisions about seawalls, relocations, and coastal planning for generations to come.